Now, before we go on to treat the Gaussian pulse with dispersion, I want to step back and just look at the recipe we're going to use. In fact, it's the recipe we've been developing up to this point. The starting point is the shape of the wave at time equal to 0. So we've got some function of the wave in space, and it's going to have a Fourier transform which is f of k, again at time equal to 0. So we can write the relationship between the function of x and the function of k like this, using an inverse Fourier transform. We can write f of x at time equal to 0 as an integral over all of the k components of the wave multiplied by the kernel e to the I kx and integrating over dk. Now, to find the shape of the wave in space at a time t, we need to rotate each k component with the right phase, and the phase depends on omega. So the function f of x at time t is going to be this inverse Fourier transform, but now we're adding this phase term e to the negative I omega t, and this is the phase we have to multiply each of these k components by in order to propagate the wave forward over a time t. What's omega? Well, for dispersion-free waves, omega is equal to c times k. So we can replace this e to the I omega t with e to the I ck times t. Now, if we were to have dispersion, then omega is no longer equal to ck. Omega is some other function of k, not just a linear relationship, but some other more complicated relationship. So we write omega as some function of k and put that into this phase shifting exponential. So we get that the f of x and t, this is the wave propagating in space and time, is given by this inverse Fourier transform now with this phase term e to the negative I omega as a function of k times t. And so this single transform, this single inverse Fourier transform, gives a function of space for a single point in time t. Now, if you want to make an animation then of this function, you have to do this integral at every time t that you're interested in. So I've called this recipe 1, modelling the shape of waves in space via a transform in k. There is a second recipe we can use to treat a slightly different situation. So what if we have a situation where, for example, we are measuring the amplitude of a sound wave with a microphone. This microphone will be at a fixed point in space, a fixed position x, and we're interested in the shape of the wave passing that fixed point in space x, and this wave will have some function of time. So we're going to start with a wave that has some function of time. We'll start it off at x equal to 0, and we want to propagate this wave to some new position in space. So we're starting with some function of time at x equal to 0 and propagating it to some new position x where, for example, our microphone might be sitting. So in this case, we're going to do a transform from t to omega. So we're going to model the shape of the waves in time via a transform in omega. So starting with at x equal to 0 and transforming to omega, we can write that the function of time at x equal to 0 is given by the inverse Fourier transform of this Fourier domain function integrated over the kernel e to the I omega t d omega. So exactly the same formulation as before, but instead of using k's and x's, we're using t's and omegas. Now, to find the shape of the wave at the point in space, we need to rotate each frequency omega, each temporal frequency omega, with some correct phase, and that phase is going to depend on k and x. So this function f of xt is now the inverse Fourier transform of all our little Fourier components here as a function of omega, but rotated now with e to the I kx. What's k? Well, for dispersion-free waves, k is equal to omega divided by c. So we could write f of xt in a dispersion-free case as this integral here, where we're integrating over d omega, and this is a complex exponential giving a phase shift which is linear in omega. If we have dispersion, we need to write k as some function of omega, which is no longer linear. So we've got k is equal to some function of omega, and then we have our integral to give f of x and t like this. So this single transform here gives you a function of time at a particular point in space. And you can see why I use recipe1 to build the animations I've shown in this video, because these animations, what I'm showing is the shape of a wave in space as it progresses in time. So I can do one Fourier transform per snapshot in time. To do something similar with this formulation here, I would need to paste together my integrals in a different sort of way, which I personally find more complicated. But there is a good reason you might want to do this transform. As I motivated at the beginning, if you want to monitor a signal passing a particular point in space, this is the transform to use. If you use recipe1, then you would have to calculate a new integral for every time and then put in your value of x. And in fact, you're doing too much work then, because you're computing this entire function over all of x and t when all you wanted was a particular function of time at one point in space x.